Let's talk about the comparison test. So just to set the stage, we are learning a variety of tests in order to determine whether an infinite series converges or diverges. Now, I want to motivate our comparison test with the comparison theorem that we saw in the improper integrals section, 7.8. Okay, so if you look at this picture on the left, you have uh, an infinite region of integration going from a to positive infinity. You have two continuous functions, f and g, like this, and you have that f is always bigger than g, which is always bigger than 0. And when you have this situation, we can say a couple of things. If the area under the bigger function f converges, then the area under g also converges. So that's represented with part A over here. If the smaller area under g diverges, then this bigger area under f also diverges. So this comparison theorem for integrals really provides motivation for talking about, um, the convergence of series. Okay, so I frame it a little bit differently. I like to use a different visual. I'm going to explain things by using a balloon analogy. So I'm going to have the number 0, and then 0 is going to be the lower bound, and then I'm going to have the smaller series be an, and I'm going to have the bigger series be bn. Okay, so instead of comparing functions, we're comparing series. And the way that I think of it is, in terms of my balloon analogy, I imagine the series being a balloon. Okay, so if the series converges, this means that the balloon collapses to a point. Okay, so if I were to draw a picture of that, it might look something like this. I'm going to draw a circle to represent my balloon, and then when it collapsed to a point, I'm going to draw little arrows kind of collapsing into the middle. So you can think of balloon convergence as being crushed to a point. If my series diverges, then I imagine that my balloon expands to infinity. Okay, so do I represent that with the following picture? I draw my balloon, and then I have arrows kind of going outwards. So these are opposite images. Okay, so what I want to do is I want to basically use the different colors for my balloons, and that kind of corresponds to the different colors we have for F and G here. And I want to think of my convergence being the balloon gets crushed to a single point, and divergence meaning the balloon expands out to infinity. So how can I represent this scenario with my uh, my two red and blue balloons? Well, let me draw a couple of situations of the comparison test here. So the smaller balloon is going to be AN, so I'll label that in red. So let me draw two pictures like this. There's AN. And then our bigger balloon is going to be the BN balloon. So let me draw a circle representing BN and a circle representing BN. like this. Now, what's it going to mean when Bn converges? We want to see what that means. Okay. And when we look at our picture, Bn converges, that means, it gets crushed to a point like this. Okay. What does that say about An? Well, since Bn is bigger and Bn is getting crushed to a point, that means that my series represented by An also converges. Okay. On the other hand, what does it mean when my smaller series An diverges? Well, An diverges means that this smaller balloon is exploding out to infinity like this. Okay. So when An diverges, what that's going to mean, that's going to imply that the outer balloon, Bn, also diverges. Okay. So I hope you can see with this analogy how the situation is very similar to the area under the curve in the integral situation. And I guess key to the idea of a comparison theorem is we're going to need uh, a collection of series to compare to. In other words, we always compare an unknown series to a known series. We always compare an unknown series to a known series. So what are the series that we know? Well, one of the series that we know geometric series. And those series are kind of the form summation a times r to the n minus 1. And we know that this converges if the absolute value of r is less than 1. Okay. What's another series that we know well? We also know p series. So p series is something like the summation of 1 over n to the p. And we know that these series converges if p is greater than 1. So I'm going to mention one series in particular, just in parentheses. Remember the harmonic series, which is summation of 1 over n. This series diverges. That would be when p is equal to 1. Okay? I just feel like the harmonic series is such a special series that we want to explicitly remind you that it diverges. All right, folks, we'll look at some examples in class. Take care.